Okay, hello everybody. Good afternoon for those here in America and good evening for those in Europe. So today we have the pleasure to have, let's see if I can pronounce it correctly, Manuel Sanjurjo Rivo.
It is okay.
Good.
It's good. Yes.
Manuel has a degree in aeronautical engineering and a PhD in aerospace engineering from the Universidad Politécnica de Madrid, Spain. And currently he is associate professor at the Universidad Carlos III de Madrid. So it's good to have you here, Manuel. And so the podium is yours, please.
Okay. Okay, thank you very much for the introduction, and thank you for, as I said before, thank you very much for the invitation to deliver the seminar today for you. So thank you for inviting me. Thank you for attending. If you don't mind, I'm going to share now my screen.
Yes, please.
Yeah. And let's see if you can see. If you can see my presentation.
Yes. Good. It's okay.
Okay, perfect. Okay, so so the idea of the seminar today is to try to give you a flavor of which are the research lines at my university at UC3M that now are related, let's say, to the exploration of celestial minor bodies. No? And the focus would be to talk about the efficient modeling of gravitational fields, but also a couple of applications, engineering applications for these efficient modeling. So in these 40 minutes, I will try to cover the points that we have here as fast as possible. As I told you, the first point would be to talk about these gravity models of celestial minor bodies, and then the engineering applications would be trajectory optimization, navigation using artificial intelligence, and robust control. And then finally, one slide for the conclusions. So here, if you want, in this introduction, what I'm trying to tell you is that the lines of research that I'm going to present today is not all we are doing at UC3M related to Spaceflight Dynamics. So then here you have a couple of other things that we are doing. So we are working in the optimization of low thrust trajectories. We are doing also orbit determination in the framework of space surveillance and tracking. And then the line of asteroids, as I told you, this is the line that we are going to see from now on. And finally, simulations of space dynamics, in which I collaborate with Gonzalo Sanchez and also with Gabriel Roberts. So why it is interesting from an engineering point of view, the analysis or the study of the small bodies or micro bodies. So this is something that, as you may know, is on the rise. The minor bodies are quite interesting from many different points of view. The main scientific contribution would be to understand better the building blocks of the initial solar system. But apart from that, we have also missions that are interested in the assessment of if we can exploit the materials that we can find in asteroids or comets, well, asteroids. But this, from an engineering point of view, present a number of challenges. Here you have some of them. For instance, environment is in general uncertain. We have a time delay if we want to do operations from Earth. And also we have to be aware of the fact that we need to have failure models that can recover from a failure, from a minor failure. So there are plenty of room from improvements, and there are plenty of challenges to address in this area. Starting with the first one is how can we model the gravitation that we are going to, the gravitational acceleration we are going to find close to an asteroid with an efficient model. Efficient, why? Because we are searching for some degree of autonomy, so we need lightweight models to be run, if possible, on board the satellites. So we are going to follow first different approaches that are used, and this is, let's say, the state of the art. So we have three big families: polyhedron, spherical harmonics, and mascons, and then some analysis with selected results. So, I mean, this is something that is familiar for you. We have a celestial body like the Earth, and we have to come up with gravity model in order to first understand, but then also to be used in propagation, dynamical propagation, for instance, on board a satellite. So depending on which is the accuracy that you need and the computational power that you have, different models are available, and different models are, let's say, good or the efficient solution for the problem that you have at hand. What happens with an asteroid like this one, that is Cleopatra, no? That it has a shape that is like a bone. No? Then the models that we have used for celestial bodies that are close to a sphere starts to fail, no? or they are difficult to use, no? As we will see later. But what we look for in those cases is, again, no, to be accurate, to be fast, and to have a low memory footprint. Again, searching for some kind of autonomy on board satellites. We have many models in the literature, very few model reviews. One of them is in the PhD thesis of Gabriel Bordelés. Here we have, I brought here another review for, as I told you, no, these different families. No? The first family is the polyhedron model that was proposed for the first time in 1997 by Werner and Shears. And the idea is that this model that is analytical, so it is able to produce the gravitational potential of the asteroid, or outside the asteroid, of course, with an analytical formula that is highly accurate, but with with a big computational cost, no? And a big also memory footprint. So it's kind of we are going to use, in fact, this model as the benchmark. This is our for a irregular shaped minor body like this one. The polyhedron model is usually used as the benchmark, but from a practical point of view, is not a model that can be in general, or is difficult to be used on board, or for fast computation of trajectories, for instance. Second option, spherical harmonics. As I mean, this is familiar, I guess, for you. We have these functions with a certain maximum degree, that is the truncation of the series that we want to consider, and then the spherical harmonic coefficients that are the coefficients that depends on the body, and that let's say the unknowns that we have to solve for in order to have a complete model of a complete gravitational model of the object. So here, for these spherical harmonics, the accuracy in general is of course, it depends on truncation that you are considering, but it's still still can be high. One of the problems, one of the issues with these models is that it cannot be used within the circumscribing sphere, or better, we can say it better, saying that the convergence is not guaranteed in this area. And for close proximity operation of asteroids, this is key. No? We need something that works when we are approaching a landing, for instance. This is within the framework of spherical harmonics. This is a work that was done by a graduate student, García Bonilla, and with the collaboration of the PhD Pablo Machuca. And the proposal is to try to optimize this or how to compute this spherical harmonic coefficients in an efficient way, using basically the information of the gravitational acceleration at certain reference points. So the idea is to try to get the solution using this information, and to do that, what we are going to use is to try to Taylor expansion of this gravitational acceleration, and using a Newton-Raphson method. So it's kind of something simple to try to solve for the coefficients. So in this case, we have that the gradient of the gravitational acceleration is our J. No? So what we want to is to solve for this delta U, and this is an iterative process that we can iterate till a convergence. No? So as a summary of spherical harmonics, what we can say is that, again, no, it's not good, or it's not possible to use a model of spherical harmonics close to the surface, and then increasing the degree, we increase the accuracy at the cost of decreasing speed and increasing the footprint as one can expect. As an alternative for polyhedron and spherical harmonics, we see the rise of mascon models in the last decade, let's say. So basically, here is the idea is similar to if we have a sphere, we can approximate quite well the gravitational potential of this sphere by a point mass. If we have a binary, we are doing the same. What happens if we have something like the Cleopatra asteroid? So what we can do is something that is kind of similar, no? To approximate the volume of this minor body with small spheres, and these spheres with point masses. So with that, what we come up with is that we are describing in a discretized way the gravitational potential of the asteroid. Another thing that I haven't mentioned is that the issue of the density, right? So the idea is that, for instance, the polyhedron model that I mentioned before in 1997, this model considers that the density is uniform along the asteroid. This is something that the asteroid, the minor body in general. This is something that is not, it cannot be given for granted, of course, and this is something that we have to take into account to assess the accuracy, again, to assess the flexibility of a model to provide the desired accuracy. Principal mascon models can provide with this flexibility. And then how can we locate the mascons within the volume of the asteroid? So the first guess and let's say the straightforward way of defining the model is using a uniform grid. As you can see here, it was first presented in proposed in 1996. But then there are evolutions of that. And here you have that in 2016, Simon Tavel was presented this idea of combining spherical harmonic model with mascons. So it's uniform grid plus one large mascon. And in the same line, this student, Juan, proposed to use more than one large mass to be combined with the mascons. Okay. So one option then is to have a uniform grid. Another option is to have a structures mesh. There are mainly two that are widespread. The first one is this one, proposed by Chanu et al. In 2015, and it is that we define a tetrahedron with the center of mass of the asteroid, and then we place a point mass that is centered within this tetrahedron. So we can do it for all the phases of the model and obtain a series of mascons forming a hollow shape, similar to the shape of the asteroid, like this one. So, and then additionally, the Chanu et al. Proposed dividing each tetrahedron linearly in 3 volumes. So we have 3 concentric layers. This concept was extended by Juan and include other options like 2 linear layers or 3 layers, but with cubic root distribution. Sorry. So in this way, the advantage of these cubic root layers is that you have more mascons close to the surface. That is, in general, something that you prefer to have. Then, unstructured tetrahedral mesh mascons is something that was recently presented, and here you have the reference is Perla Heat in 2017, sorry. And in these animations, we can see the first kind of mesh that was proposed. That is a tetrahedral mesh. On the left is you have a mesh volume with a moving cutting plane, and on the right you have the mascons that are generated from the equivalent slice of the mesh. So what you see is that the mascons tend to concentrate near the surface. As I told you, is something that in general you prefer to have. And also they suggested polyhedral cells. That is similar, but well, I mean they are bigger. The cells are in general bigger. Another approach was the optimization. So instead of just place the mascons using either a structured grid or an unstructured grid or something that is, if you want, given a priori, what we can do is to have the distribution as an outcome of an optimization, and in particular as a genetic algorithm optimization. So the good option, or the good point for this is that you don't need a particular initial guess. The problem is that you have very slow convergence. In a similar fashion as we saw for the spherical harmonic coefficients, we can use this inverse problem optimize, that is the proposal of this student, Juan. So we have this information at the reference points, the gravitational acceleration, we have the position and mass of each mascon as the variables that we want to optimize. And then what we are doing is just to estimate which is the distribution of mascons that best adjust these measurements that we have, or the gravitational acceleration at each of the points in which we are computing the gravitational acceleration. So with this, well, I mean, this is an iterative process again, but it's a problem that can be solved using the same Newton-Raphson approach as I mentioned before. So as a summary of the mascon models, what we have is that, again, no, it's similarly as the spherical harmonics. If we increase the number of mascons, we increase the accuracy, decrease the speed and memory, and the memory footprint is increased. So some selected results of the analysis. I will go fast here. So the idea is that we compare which is the performances of the different methods in a similar framework. So the framework is we are using, as I said before, the polyhedral method as the benchmark, and with that we are computing the gravitational acceleration at certain reference points outside the asteroid. No? And then with that we can compute which is the average relative error for these set of points. And here you have the comparison of the error of two spherical harmonic models, changing the maximum coefficient degree. So as you can see, the analytical computation follows a exponential trend, while the coefficients obtained with the optimization proposed cannot keep pace with that. No? And this is something that I mean, in principle makes sense, no? Because at some point for degrees higher than 20, the number of coefficients that you have to estimate is increasing too fast, and the optimization usually, or depending on the initial guess, you can have trouble to find convergence. So yeah. Then we compare the performance of the radial mesh mascons, and with that, what you can see is that the uniform grid, and then including 1 or 3 large mascons, are providing errors, average relative errors that are depending on the situation, but are providing fair results. But if you want to go to something with less than, let's say, 2% of error, then you have to go to a number of mascons that is almost prohibitive. So well, here you have again, no, which are the references which you can include the different proposals and the comparative and the comparison of the different approaches within the same framework. So, and here, just to refresh your mind, what we mean by uniform grid, 1 large mascon and 3 large mascons. The difference among them, as you can see, are small, and the trend is similar for the 3 of them. If we go to radial mesh, what we have is the Chanut proposals and then Garcia Bonilla. Again, the trends are quite similar. Here, the scale is different, as you can go back. The scale of the number of mascons is different. So what we can see is that they seem to have an asymptote, and the asymptote is around something is 2%, 3%, no less than that. Even going to something like 3,000 mascons. So, well, here the proposal, and here again, which are the different options that we have considered in this analysis. So again, the trend is quite similar. So, from the point of view of, if we want to compare, let's say, all of them at the same time, what you see is that all of them have similar trends. So it's if we include here the unstructured tetrahedral with tetrahedral or with polyhedral, and then the unstructured with 1 layer or 3, or the grid plus the 3 large masses. Or the genetic, that in principle is the best option. That makes sense again, no? Because in principle what we are doing is to optimize the number of mascons to have a given relative error. The idea is that you have a performance that is quite similar and with a certain asymptote close to 2%. And then, those two are the best solution. And then when we compare with this inverse optimized, you do this optimization of optimizing the mass and position of the mascons, what you have is something that is much better, let's say. So what we found is that we can increase a lot increase the average relative error. So having a better performance with a number of mascons that is much smaller. So we have, of course, to do a pre-processing to search in a certain body, which is the optimized, which is the optimal distribution. But once we have the optimal distribution, the number of mascons that we need to describe the gravitational field of the body is smaller, much smaller. And here you have for 300 mascons, which is the relative error. And as you see, the problem is close, or the higher error is close to the surface. If we want to use 300 mascons, for instance, for close proximity navigation that is beyond 1 kilometer, then the error that we are committing is probably we are the gravitational model is not the main source of error, let's say, for the dynamical model. Okay, so this is only taking into account the accuracy of the method, but we have to consider as well which is the evaluation time, or as a proxy for which is the computational cost, and then the memory footprint. And here we are comparing the polyhedral model, that is the benchmark, and as you can see, the error is 0 by definition because it's the benchmark, but with evaluation time that is high, and then the memory footprint that is also high. We are comparing here the spherical harmonic with maximum degrees 5, 10, and 20, and then also these inverse optimized mascons, the number of mascons. So what you can see is that for mascons outperforms spherical harmonics in any case. And then when we go to memory footprint, what we have is that the trend is similar for both, for spherical harmonics and mascons. Although for a given average relative error, we can have slightly less memory footprint for mascons. Okay, so with this, I finish this review of the minor body gravity models, and we can go to the 3 engineering applications that they are going to be faster. So if you want, is why we have done this review of the literature of the gravitational model, because we are using them in trajectory optimization, navigation, and control. So taking for trajectory optimization, basically what we develop, or what we have developed at the department, is a tool that is known MOLTO-MB, so it's multi-objective low thrust optimizer, and MB stands for minor bodies, and it is the structure, or the architecture has 2 steps. Step 1 is something that is multi-objective and is based on a genetic algorithm, so you explore more or less efficiently all the field of solutions that you have available. In this case, for MOLTO minor body, the design is shape-based. So we are using a surrogate model for the dynamics. And then this step 1 provides an initial case for a second step in which you have an optimizer that is gradient-based and single objective. That uses Hermite-Simpson collocation, that is a technical. So I'm going to go through this surrogate model just quickly, because what I wanted to show you is just how this works. So basically, what the idea is to have something that is easy to describe. So here you have an initial position, initial velocity, just with one parameter, we can have a family of something that is known as generalized spirals that goes from a theta 0 to a final value of theta. So if we want to describe an arc around orbiting around a minor body, what we can do is to divide the trajectory into, for instance, 3 arcs. One is a generalized spiral that with 1 degree of freedom. Then we have the limit for the first spiral, the limit for a second spiral, and then a ballistic connection between both. And finally, a control parameter at the third spiral that is used to match the desired final condition. So what we have is a way of connecting two position vectors using generalized spirals in a similar way as a Lambert problem, but here we have 3 parameters open that allow us to explore to fly this arc, which is the acceleration that we need, and compare it with the gravitational acceleration. No? The difference is the thrust acceleration, and what we want to optimize is the thrust acceleration. So we want to minimize the amount of thrust that we need to follow the arc. We have also the possibility to include the 3D, so not only in a plane, but also out of plane, and it is decoupled, so it's a good thing. And with that, we have 5 coefficients to explore and to optimize in order to have the minimum delta V between 2 position vectors around an asteroid. And when we have, I'm not going to enter into this. I prefer to go to an example. So the idea is that you have an asteroid or a minor event in general. You have your initial position, your initial velocity. You want to go to this area here, to this area that has. You want to explore this area with red dots that we have in the other side of the asteroid. And then you can do this analysis, the analysis of where to, with a camera, right? Where I can place the camera, when I can pass by, in order to see this area. And once I decided which is the point I want to go, I can just pose the problem in this way. I want to go from R0 to RF. And I know the initial velocity. So which are the options that I have available? So if I run MOLTO-MB, I arrive to this Pareto front, in which we have here the mass consumed and this the velocity magnitude. You have also the final time, so you can also consider fastest trajectories among them. So how this works? So once we have computed the Pareto front, so you can select for instance, the minimum mass trajectory between these 2 points, and which is the position in the Pareto front, and then which is the aspect that it has in the asteroid reference frame. If instead of mass we want to have final time, we have similar. This is basically similar. Another point of the Pareto, another trajectory. We can also go directly to the Pareto front and say that we want one specific solution, and then we can depict the solution and see the table with the magnitudes below. And finally, we can maybe want to, for instance, weight. I want to have something that weights 20% the mass factor and 80% the velocity factor, and we come up with which is the solution. And this solution is easily used as the initial guess for the next step. So we have, let's say, this is the solution that we have with reduced dynamics, or with the Surrovit model for the dynamics. But once we have that, we can go for a single objective optimization, and then go for this solution of the step 1, that is the Surrovit model, to the solution with the full model, with the mascons model for the gravitational field, and obtain the solution. So what we have here is that we have a final velocity that is smaller than the one that we consider in the reduced model, but at a certain cost, because we have doubled the mass of fuel in percentage. Okay, so this, let's say, it's a capability that we have with MOLTO, and what we and this is in principle something that can be used for preliminary design of which is the close proximity operations around an asteroid. Things that usually we don't have a good gravitational model for that case, in that case, but still, no, could potentially be used. And then the second point has to do with navigation. So which is the idea here? The idea is that we can use convolutional neural networks for optical navigation of minor bodies. So, why? Because CNNs have been used or are used to do for similar purposes on Earth, and they are lightweight and they have, let's say, fair performances. It's something that maybe not is not something that provides you with a high fidelity solution or an estimation that is the best that you can get, but at the same time you have a certain robustness, because the network can respond to different objects even if they are not trained exactly with the object that you have considered. So from as I told you, take into account that when you are planning the mission, you don't have usually the shape, the right shape or the features of the surface, for sure, of the minor body. Then having something that can be trained with similar shapes and similar features on the surface, it could be interesting. And then within CNNs, we have like two families. One is classification, so networks that produce classification. So what we can do is to split the regions around the asteroids in a number of them, and these networks are able to identify in which of the sections we are. And then regression, that consists on, you are using either the coordinates or the Euler angles of a certain relative orientation as the variables to be estimated as a continuous variable. So it's something that is continuous. And in this work, that is, by the way, sorry, because I haven't mentioned, is the first author is Alfredo Escalante, that works for the European Space Agency and is doing the PhD at our university, and also Pablo Gilino, that works for Clepsydra, that is a Swiss company. Okay, so the idea in this work was to explore the possibility of using CNNs for navigation around minor bodies, right? Either using classification or regression. So which are the problems that, as here you have images from 69P Churimov, sorry, Gerasimenko. I don't know if I'm saying it correctly. Hopefully, yes. The idea is that here you have different images taken from Rosetta, and as you may understand, it is difficult to try to orient yourself using just the information coming from these images. And which are the challenges here? Mainly three. One is the scale variation, depending on the distance that you are from the minor body. The viewpoint variation, that in this case is really, really important because the shape is completely different. And then the illumination conditions that makes also that the shape can change a lot also from that. So those are the challenges. The good thing is that for let's say earthly problems, we have the same issues. So we have viewpoint variations, illumination conditions, scale variation, make the work of these networks difficult. But it's something that we know how to manage it, at least on Earth. And then what we did is to we went for the first, and really the first problem is not if the network is going to work or not. The problem is that you need a large set of images to feed or to train the network, and those are not available. So in here you have a rough estimation of which is the number of images that we need for training and test, and this is from 10,000 to 50,000. So what we have is few thousand of images, and with limited illumination and viewpoint conditions. We need if we want to work with CNNs, we need to train properly the network. And for that, what we did is to develop render synthetic images. So what we did is to in a synthetic way, produce new images from the ones that we have, and using, as you can see here, Gaussian noise, random illumination condition intensity, etc. And with that, we could get the amount of images that we need for the training and the testing. And then coming back to the question of classification or regression, the thing is that for multi-class classification, so the first option, the accuracy depends on the level of discretization, and the number of the larger of the number of levels, the larger the estimation error. So the point here is that if we want to discretize the possible areas in an increasing number of sections, then the error that we are going to commit is larger. On the other hand, the regression estimation, the regression position estimation, the problem is that it's very difficult to train for global position estimation, because you have, as taking into account that it's continuous, you need a really large set. So the thing is that, and also regression shows better accuracy estimated the position of 4 regional sets. Once we know that I'm in this region, then regression networks works better. So the solution that we found is these 2-level hybrid CNNs, in which we have a high-level multi-class classification. We select in which area we are, and then, well, we have again another high-level regression for the shift the images, so to put the images in the center, let's say. And then a low-level regression for pose estimation. For once we know which is the region, within the region, which is the actual relative orientation. And here you have a demo that is can be seen in the Clepsydra website for again for the same, for the comet 69P. And here you have which is the error. What you have seen is that, well, the error in general is in something that is 0.025, so it's not so bad. I mean, it's not high precision, but it's something that is good enough, let's say. And what we have detected is we have trouble when we go from one region to another, and in fact we are working on that. But in general, it's something that is, let's say, it's a proof of concept that these kind of architectures with CNNs can work for optical navigation in close proximity of Federation of minor bodies. And finally, just a couple of slides more to talk about robust control. The idea is that, as I told you, that we are in the direction of gaining autonomy in space. So for that, what we need is an increased turnaround time and simplified mission design. So what we need is robust guidance and control laws to gain independency from ground-based control. And here you have possible methods, Convex optimization for guidance, or machine learning, reinforcement learning, something that in principle would like to explore. But so far, what we have done is to use Convex optimization, as I mentioned after. No? Here you have, well, specifically for an asteroid descent, we have plenty of challenges. 3 of them are maybe, let's say, the most important, or what we consider the most important. So it's the non-linearities, the uncertainty in measurements and models, and also the collision avoidance or the hazard detection. So, I mean, without entering into much details here, the idea is that Convex optimization is something that can give us the performances that we need to have something that is accurate enough to produce the control laws that we need in a robust manner, with a cost that is something that can be handled on board. So we went for quadratic programming, because we have fast solvers and has been extensively used in model predictive control. We are going to use robust model predictive control, and within robust model predictive control, we have, let's say, deterministic or stochastic approaches. Again, I'm not going to enter into much detail, but the idea is that we have selected 2 tube-based robust model predictive control, and the idea is that once you have a certain instant of time, you are here, you have a certain trajectory that you want to follow, and you have the error, or you have the noise, if you want, and you know the boundaries of this noise. No? So you have a good knowledge of which is the maximum noise that you can have during this time horizon, and you come up with the optimal solution for the control that provides us the guarantee that you are going to be within a set of possible states. So basically, only advantages and with respect to the conventional approach, the idea is that we have constraint satisfaction. So if we want to arrive to a certain spot and land in a certain spot on the surface of a minor body, we can do that. It is computationally simple, and we have a high degree of autonomy. The problem is that we have linear performance in a linear environment, so this is something that is going to be to penalize the amount of fuel, no? The amount of propellant that we need in principle, we need to consider for the maneuver, and the performance is also subject to tuning. Here you have a scenario, typical scenario in the literature, the power descent on Eros, with these conditions. The idea is to have a soft landing on a surface. Mass is big, but still, no. Have 2 tons, 60 newtons, that is also a lot, and 400 seconds. So it's like with chemical propulsion. And we are using this gravity model using mascons. Here you can see which is the robustness with respect and against the uncertainty that we have, and this is the difference with respect to the different imposition with respect to the target trajectory, and the different controls. So the control that in principle we require, let's say, from a guidance point of view, and the actual value of the control. So here you can see that this we have a robust solution, but with a penalty in the cost associated to it. And but it's again one way of showing that is robust is that we are feeding with different initial conditions for in the area in which we have landing. No? So we have the landing, and we are able to arrive to the point with a velocity that is within the boundaries, the constraints that are selected a priori. And with this, I finish. I'm sorry because I'm in the 50 minutes. In the 15 minutes option instead of the 40, but the idea is that what I wanted to show you is that we are at the department developing a set of tools for a comprehensive design of GNC systems for minor body exploration. It's an area of intense research in general, so not only in our department, but in many different engineering departments, and I think that we will see important contributions in the next years in this area. And then it's also an area in which we, but not only we, also other research groups are collaborating with industry and other research institutions. So again, no, with this I finished. Sorry, because the target was 40. But if you have questions or if you want to have a discussion now, I'm more than happy to try to answer and to talk with you.
Okay, Manuel, very good presentation. I think you made a huge presentation in the sense that you covered so many aspects. So it's okay with time. Don't worry. It's good. It's great. And I liked very much the first review you made on the models of gravitational models. Very, very interesting. Do you have that those material published in?
Well, yes. I haven't mentioned, but yes, the review was presented by this student, by Juan García Bonilla, in the International Astronautical Congress in 2021. So, I mean, if you want, I can share the publication. Also, for more details, the bachelor thesis of Juan has a lot of details on many different options that he tried, starting from the literature and the comparisons that he made. So, I mean, I can share this. That is public, of course.
Yes, please, because we have a few works we are doing using these models, and that would be really interesting to improve our approach. We usually use mascons, but I like that idea of composing with larger bodies inside. So that would, I believe, would make it much faster, and preserving the precision, the accuracy of the model.
Yeah. This is something that well, it is not our idea. It was presented by Simon Tarribel from CNES, and we found it interesting to explore. And in fact, it compares well with the state of the art of mascons.
Okay.
So, yeah.
You said the work was presented in IAC 2021? Last year?
Yes. Yeah.
Okay.
Yeah, both. Yeah, in fact, the other one, the navigation part, also was presented in the International Astronautical Congress, and then the last one. But by the way, I think I haven't mentioned the first author. That is Thomas Freckhow. He's a PhD student here, and this work was presented this month in Berlin in Euro GNC in a conference, in a Euro GNC conference.
Okay. Are you going to attend the IAC this year? No?
Yes, hopefully yes.
Perhaps we can meet there. Perhaps you can meet presently there. Okay.
Perfect.
Good.
I mean, the problem is the price of hotels in Paris. now now. This is the main problem now. But yes, we have some works accepted for presentation.
Oh, good. Okay, so we are open for questions. Anybody would like to make a question or comment? Oh, actually, I have another one. You said you have this collaboration with the industry. Are you having collaboration with the industry now already towards this mining of asteroids?
No, mining, no. No, but the thing is that as far as I know, the company, there were like 3 or 4 companies that settled down in Luxembourg.
Yeah.
But as far as I know, all of them are already in bankruptcy. So I think it's I mean, I'm not collaborating with them. But it's
That's a good news.
the good news. But for instance, with this artificial intelligence for navigation, I'm collaborating with, or we are collaborating with this company, Clepsydra, based on Switzerland. They are quite interested in general in using artificial intelligence on board satellites. And also European Space Agency is slowly, but I think at a certain pace, it's pushing in this direction. So yeah. And then the other collaboration that I haven't mentioned is there is an industrial PhD, a PhD that is done in collaboration with industry, with a Spanish company, Deimos Space.
Oh, Deimos.
Yeah, and they are doing. I mean, they have a software for these kind of missions, and they are developing additional. For instance, they are developing with artificial intelligence an algorithm that is able to do this hazard avoidance. Well, hazard detection and avoidance.
Okay, good. So really a very dense work, very detailed work. That's good. Great.
I mean, the thing is that there are students working on that. So there's PhD students. So that's why I can present this amount of work. Otherwise, of course, only on my own, it's not possible, of course.
Yeah, it's the same here. I do almost nothing. I just tell them what to do. That's the way. Okay, good, great. Okay, so now we are open. Anybody would like to make a question or comment? We here usually does not go much deeper in the engineering approach. We're more astronomical view of the problem.
Yeah, I know.
A lot of superposition on what you showed.
Yeah, I asked Gabriel a little bit for how, I mean, because again, it's in our case it's the other way around. We are an engineering department, so the core is on the engineer in the application, let's say. But I understand, that maybe from the work that we are doing in this line, maybe the review of the mascon, well, in general, the gravitational models is the most important for you, and that's why I try to go in more detail in this area. And in fact, if you don't have any question for me, I have one for you. Because one thing that we have, I mean, I presented here this inverse method to knowing the gravitational acceleration or the gravitational potential at certain points outside the asteroid. Try to optimize the mascons inside. We thought that maybe this can be used for trying to recover the mass or the mass distribution of the asteroid or comet, no? The minor body. But then we saw that the literature for that is kind of different. So the methods are similar, but different. No? So the problem of having in situ measurements of the gravity or potential, and from that information infer the mass distribution of the minor body is kind of different and is not I don't know if and mascons are not really used a lot, have not been used a lot in for that, no? for this.
No, they usually they don't use that. That has been made, let's say, very extensively on the moon, and
Okay.
they use even the name mascons on the moon, but just to say different regions of higher density, and they call mascons.
Okay.
But actually, it's you have let's say spots of higher density. So
Okay.
it's
okay. Okay.
it's,
So
they use the word mascons, but it means you have let's say different dense regions with spots on that. That's very common in studies of the moon.
Huh?
I think the L-Cross mission, I don't know if you know the L-Cross mission, map it, and they use that approach, but they don't use the mascon as we use and you showed here.
Yeah.
It's
No,
different.
that's it's because again, no, it's it is the typical. Well, thank you, by the way, thank you for the answer. But it's the typical thing that something happens. You are using a method that for something that is in so for modeling, and then maybe we can use the same similar approach for science. But then you find that the families of solutions is different. So you have to start over and see and start with a literature review of how to obtain the distribution knowing the in situ measurements of the gravity. And and it's
but I think perhaps there's a way to use as you do. I think it's a matter of finding let's say equivalent measures. I think but it's a good idea.
Yeah. Now the problem is to find. Juan García Bonilla already graduated. So the problem is not find the mass distribution, but find a student that continue in this line of work.
Okay. So, but just commenting on the engineering aspects, we are trying to move towards this. So, what you presented, it's stimulating. So, I think we have some students and some people that wants to go towards the engineering aspects. So, we have to start moving towards this direction. That's good. Okay, so I think we have to thank you. Thanks very much. It was an excellent presentation, and it was nice to meet you. See, let's see if we meet in Paris in a few months.
Hopefully, yes.
Okay, let's hope. And
thank you for having me and for the invitation. Thank you very much.
Okay, thank you. So now, just before we finish